Hello and welcome back to another daily math video. Today we're asked a question from AHSME year 1981, number 30. Alright, okay, so it's number 30, so we know it's going to be tough. Let's read the problem and see what we're actually dealing with. So it's giving us the roots a, b, and c, d of the polynomial x to the fourth minus mx minus 3. So those are the roots of this polynomial. And it's asking us to find another polynomial, and it has to be with leading coefficient 3, whose roots are the following. And these roots that we're trying to find the polynomial with are in terms of the roots of this polynomial we're already given. X to the fourth minus mx minus 3. Alright, so how do we solve this? This looks crazy. I mean, look at all of these crazy expressions for all the roots, and it's even squared in the denominator. This looks crazy. How does the numerator even simplify? Well, alright, before we start getting carried away with how difficult this presumably is, let's first notice that because we're dealing with 4 roots over here, we're dealing with a degree 4 polynomial. Okay, and we're assuming that, okay, they're not playing tricks with us with multiplicity or anything like that, that we just have a degree 4 polynomial, similar to the polynomial they already gave us. Alright, so our second fact that we must recall is whenever we're tackling a problem that has to do with polynomials, and it's usually towards the end of a math competition, usually uses some sort of application of Vieta's formulae. So what's Vieta's formulae? Well, Vieta's formulae gives the coefficients of a polynomial in terms of its roots. So how can we use that here? Well, remember, when it's asking us to find the polynomial with leading coefficient 3, whose roots are these 4 expressions, what it's really asking us is find the coefficients of the degree 4 polynomial with these roots. So that will be very useful because given the roots, we can probably find the coefficients from Vieta's formulae. Alright, so let's first start with Vieta's formulae and applying it to this polynomial over here. So our first equation for the coefficient of the x cubed term is right over here. The sum of the roots, a plus b plus c plus d, is equal to 0. Why 0? Because there is no x cubed term. So that means the coefficient of the x cubed term is 0. So 0 times negative 1 to the third power, because x is raised to the third power in the x cubed term. And this is just 0. So this is our first equation, what it yields. Alright, so for our second equation, we take the roots in pairs. The first equation, we just took them one at a time. Second equation, we take them in pairs. So we have AB plus AC plus AD plus BC plus BD plus CD, so we take them in pairs in all possible ways, is equal to 0 times negative 1 squared. Why 0? Because 0 is the coefficient of the x squared term in this polynomial right over here. And because there is no x squared term, that means the coefficient is 0. And we have negative 1 squared here because the x squared term is raised to the second power. The x is raised to the second power. And this just gives us 0 once more. Interesting. And for our third equation, we take the roots in 3. So we have ABC plus ABD plus ACD plus BCD is equal to the coefficient of the x term. And that's just negative m. So negative m times negative 1 to the first power, because x is raised to the first power in the x term. And this is just equal to m, because the two negatives cancel. And lastly, we take the roots in group of 4, and we get the product of a, b, c, d is just equal to the constant term, which is negative 3. Negative 3 times negative 1 to the 0th power, which is redundant because this is just 1. And this just simplifies to negative 3. Alright, so we already have the information we need to simplify these 4 menacing expressions. I mean, look at them. How in the world are we supposed to solve Vieta's formulae and find the coefficient of the polynomial with these crazy roots over here? Well, of course, we just simplify them. So how? We use our first formula, our first equation, that relates the roots to the x cubed term over here. So, given a plus b plus c plus d is equal to 0, that means when we subtract d from both sides, we get a plus b plus c is equal to negative d. And Viola, look what we have over here. Negative d in the numerator. And denominator is d squared. So negative d over d squared is our first root of the polynomial we're trying to find. And this just simplifies to negative 1 over d. How nice. We can do a similar application to these three other roots, and we find that the roots of the polynomial we're looking for is just negative 1 over a, negative 1 over b, negative 1 over c, negative 1 over d. Just apply the same technique, except instead of subtracting d, subtract c, subtract b, or subtract a, and plug into these three other roots that we need to find. Okay, this really drastically simplifies it. It looks much easier to find the polynomial with these four roots instead of these four roots. It looks crazy. Okay, so without further ado, let's move on and try to find the coefficients of the polynomial with those roots over here. So again, applying Vieta's formula, it has to have coefficient 3, right? Leading coefficient 3, because that's what it gave us in the problem. And we're just labeling the coefficient for x cubed as capital A, for x squared, capital B. For x is just capital C, and for the constant term, just capital D. All right. So let's apply Vieta's formula to find A, B, C, and D, the capital letters, in terms of its roots over here. And hopefully, once we find the coefficients in terms of the roots over here, we can find this expression, these expressions, in terms of the coefficients we have over here of this polynomial that we're given. Hopefully, we can do that in the end. All right, so for our first formula, for the x cubed term, we have a over 3, because 3 is the leading coefficient of the polynomial, times negative 1 cubed, because the x is raised to the third power, where the a is the coefficient of x cubed. This is just equal to the sum of the roots. So negative 1 over a minus 1 over b minus 1 over c minus 1 over d. For our second formula, we take the roots in pairs, and we add them all up. So we have negative 1 squared, because it's the x squared term for b, times b over 3, because 3 is the leading coefficient, is just equal to, and now our terms aren't negative on the right-hand side anymore. They're positive, because when we multiply two negative numbers, the negatives cancel and it becomes positive. So this is just equal to 1 over AB plus 1 over AC plus 1 over AD plus 1 over BC plus 1 over BD plus 1 over CD. Some crazy expression. And once more, for our x term over here, the polynomial we're looking for, we have negative 1 to the first power times c over 3. Our coefficient for the x term is c, capital C, is just equal to, and then now, because we're multiplying three negative numbers, we have a negative sign in front of all of our terms on the right-hand side of our equation, because three negatives just remains a negative. So negative 1 over ABC minus 1 over ABD minus 1 over ACD minus 1 over BCD. So we take the roots in triplets in all possible ways. And finally, for our constant term, applying Vieta's formula once more, we just have negative 1 to the 0th power, which is redundant, just 1, times d over 3 is equal to 1 over ABCD, because we multiply all of these roots. Because we have an even number of negatives, so when we multiply, all the negatives cancel out, and it becomes a positive term on the right-hand side. All right, that's interesting. So let's try to find these four expressions in terms of the coefficients of our original polynomial over here with roots A, B, C, and D, where they're all lowercase letters. So don't get confused. Our coefficients we're trying to find for our polynomial are capital A, B, C, and D's, but the roots of our original polynomial are lowercase a, b, c, and d. I just did that because I don't know. They both seem to fit well. But anyways, let's try to find it in terms of the coefficients of our original polynomial we're given. So, negative 1 over a minus 1 over b minus 1 over c minus 1 over d. So what is this equal to? Well, let's look back at these formulas over here. Okay, so given these formulas, how can we find the reciprocals, the sum of the reciprocals of a, b, c, and d? All right, well, what we want to do is we want to divide by a, b, and c, and d and have 3 of the terms to cancel per each term in the numerator. And let's just try something out. Let's just try to divide equation number 3 here by equation number 4. So we have ABC plus ABD plus ACD plus BCD over ABCD. And we have this is negative because we can factor a negative on the left-hand side and we must keep it negative. So is this equal to this? Well, yes, because if you were to split up this fraction, 3 of the terms in the numerator would cancel every single time and we'd just be left with the opposite reciprocals of A, B, C, and D. So for example, for ABC over ABCD, we would get negative 1 over D. For ABD over ABCD, we would get negative 1 over, negative 1 over C. And then again here, we just get negative 1 over B, and then negative 1 over A. And remember, based on the formula we have here, this right here is just equal to M, positive M, and ABCD is equal to negative 3. So we have positive M over negative 3. And remember, we have the original negative in front because we want to make this whole thing negative to make it match here. So the negative 3 and the negative in front of the fraction cancel, and we just get positive M over 3 for our expression over here. So that means this right here is just positive M over 3 because this is just positive M over 3. And now we can solve for A. Interesting. But first, before we do that, let's solve for these other expressions over here and then plug them and solve for the coefficients later. So for here, we have 2 roots in each denominator. So we want 2 other roots to cancel in the numerator every time, or 2 of the roots in the denominator to cancel every time. So how would we do this? What would we divide by A, B, C, and D? Well, let's divide equation 2 by equation 4. And in the end, when we divide these 2 equations, in the denominator, we will always get only 2 roots in the denominator. And that's good because that matches what we have over here. So this is just equal to, this is what we have for equation 2, AB plus AC plus AD plus BC plus BD plus CD over ABCD. And what is this equal to? Well, 0. Why? Because this expression at the top from equation 2, we find this is just equal to 0. So because the numerator is 0 here, it doesn't matter what the denominator is, the whole expression is 0. Interesting. So moving on to our next expression, we have negative 1 over ABC minus 1 over ABD minus 1 over ACD minus 1 over BCD is equal to, well, this time we use equations 1 and 4. We divide equation 1 by equation 4, and in the end, in the denominator, we always have 3 roots because 1 always cancels in the numerator from each of these 4 terms. So we have negative because we have a negative in front of all of these terms on the left-hand side. So negative A plus B plus C plus D over ABCD. You can verify this by splitting up this fraction and you'll see it simplifies to this right over here. And this, once more, is just equal to 0. Why? Because the numerator is equal to 0 as well, just like as we have before. Again, is equal to 0. And remember, the reason why it's equal to 0 is because we have no x cubed term here. The coefficient of the x cubed term is 0. So that's why we have this is equal to 0. And lastly, for our constant term, we just need 1 over ABCD. Okay? So what's 1 over ABCD? Well, remember, ABCD is just -3, like we did before. So 1 over ABCD is just 1 over -3, or -1/3, because we can move the negative to the numerator. Alright, so we already solved for all these expressions. Let's plug them back in to the formulas we already had for our coefficients right over here. We're plugging them back in for these 4 expressions we already just found. So our first equation is -A/3, that's the coefficient of our x cubed term, is just equal to m/3. Second equation is b/3 is just 0. Of course, this implies b is 0. Third equation, c is just 0 because -c/3 is equal to 0. And our fourth equation is d/3 is -1/3. And just solving basic multiplication and stuff, just a is equal to -m because the 3's cancel. B is equal to 0, c is equal to 0, and d is equal to -1 because the 3's cancel once more. So, finally, we have our polynomial. We have our values for capital A, capital B, capital C, and capital D, and they go into this polynomial over here. So, our polynomial now is just 3x to the 4th minus mx cubed, and then minus 1. And that's it. We have our answer, finally. So, remember, what is it asking us in the beginning? Well, we already found our answer, but remember, we just answered this crazy problem right over here. So that means this polynomial right over here has these 4 roots right over here. So if you were to plug in these 4 roots into this polynomial, then it would make it 0. Interesting. That's really, really interesting. And if you look at the original polynomial it gave us, you can kind of see some sort of symmetry, can't you? Because the constant term here is -3, the degree 4 term is +3, and the x cubed term here is -m, while the x term is just also -m. So it's kind of reversed. Interesting, but also some sign switches as well. So we finally have our answer. This is a really interesting problem. And if you're kind of confused about Vieta's formulae and you don't really know what they are exactly, there's tons of good resources online. I might make future videos in the future on how, I might teach you a little bit about Vieta's formulae, but as for right now, I'm just pulling these out of thin air. Hopefully that you don't mind that, because I hope you've had exposure with this before. But there's a ton of good materials online that will give you some information about Vieta's formulae. So I hope you enjoyed this video, and if you liked it, please like the video, and if you have anything to share, please do so down in the comments. If you have any questions, of course, do so in the comments once more, and thank you for watching. Bye-bye.